Good afternoon, everybody. And I'm Dr. Nutan Agadi, and I welcome all the participants for today's webinar on thermal analysis. Before we go into the main talk on thermal analysis, I would request the head of SAF CRNTS department, Professor Suparna Mukherjee, to give a brief introduction on SAF on our department and the facilities that are available in our department for your use. Thank you very much. Yeah.
Thank you, Nutan.
Yeah.
I'll share my screen.
Yeah. Okay.
So I will give you a brief introduction to the sophisticated analytical instrumentation facility, SAIF at IIT Bombay, which is an open access research and development facility. And I'm Suparna Mukherjee, currently heading SAIF. So the DST funded SAIF facility was set up in 1976. And then in IIT Bombay, the Center for Research in Nanotechnology and Science was set up around 2006. And then the two were merged in 2008. So currently we have SAIF and CRNTS together. And in this SAIF facility, we have 14 major equipment. And in CRNTS, we have some IIT Bombay central facilities, which are 6 major facilities are here. And in CRNTS, we have PhD students who are working in the area of nanoscience and nanotechnology. Yeah. So currently, we have about 83 PhD students who are guided by our associated faculty members who are faculty in various departments in IIT Bombay. So more than 135 faculty members are associated with SAIF CRNTS. In the last financial year, 2021-22, we had around 1,700 users and around 13,000 samples were run during the year. Now, these are the facilities we have in IIT Bombay. You see, we have various electron microscopy facilities, the field emission gun transmission electron microscope 300 kV, then FEC-SEM, and the dual beam, focused ion beam and FEG-SEM. These are the electron microscopy facilities. In addition, we have several mass spectroscopy facility. We have the GC-HRMS. We have high resolution liquid chromatography, which is both QTOF and also orbit trap. We have both the systems. And then inductively coupled plasma MS, ICP-MS. And we also have the time of flight and time of flight secondary ion mass spectrometer, which is TOF-SIMS. And there are various other miscellaneous instruments like CHNSO elemental analyzer, then ESR, then FTIR imaging, NMR 300 megahertz, then small angle X-ray scattering and profilometer. In addition, recently we have procured thermal analysis instruments, and today's seminar is around that, the thermogravimetric differential thermal analyzer and differential scanning calorimetry. And later on, we will also be installing the dynamic mechanical analyzer or DMA. So these are some of the central facilities we have in SAIF CRNTS, which is ICP-AES, then laser Raman spectrometer, then environmental scanning electron microscope, 200 kV, and also the field emission gun transmission electron microscope, 200 kV. And we also have a 2D gas chromatograph with MS detector, and also the UV phase spectrophotometer with integrating sphere assembly. This is showing our the samples received from various parts of India and some of the neighboring countries also. As you can see, our samples are mostly received from Maharashtra, but also from other states, which the numbers are lower for other states, but still we get a lot of samples from other states also. And this is the SAIF CRNTS staff members who analyzes the samples and takes care of the facilities to keep them in good working condition. And we often have visitors from various places to review our facilities. And we have also recently have school children visit us as a part of the DST Stuti program in 2022. Of course, there were a lot of restrictions during COVID, but in spite of that, we did have a few visits in the meantime. And we also hold webinars in various facilities and their applications, just like the one we are doing today. And the webinars are available in the YouTube channel of SAIF, so one can go through it later also. And so you can also join us on LinkedIn. SAIF has a LinkedIn page as shown here. And today, as I said, we will be talking mostly about our thermal analysis instruments, the TGDTA and the DSC, which are newly installed and they will be soon made available for use. So today we will be discussing the theory and instrumentation of DSC and TGDTA and its various applications in that will be discussed by Dr. Premchnad Jain. So I welcome you to the webinar now. Thank you.
Thank you, Professor Suparna Mukherjee, for presenting the information about all the current facilities at SAIF IIT Bombay. Now I would like to introduce our speaker, Dr. Premchnad Jain. Dr. Premchnad Jain is currently working with Hitachi High-Tech Technologies Japan and holds the position of General Manager in Thermal Analysis Division. He is working in the field of thermal analysis and spectroscopy and has more than 37 years of experience in this field. He has completed his PhD from Mumbai University in the year 1982. He has published more than 15 research papers in various journals of repute. During his last tenure, he has been trained in various analytical instruments, including thermal analyzers. He had received many recognitions in the past for his marketing performance. We are fortunate to have him here today with us. Over to you, sir. You can start.
So, good afternoon, everyone. Thank you, madam, for very nice introduction. And without wasting much of time, today we shall be discussing about applications of thermal analysis, particularly DSC and TGA in various fields. Just to give you an idea, Hitachi, this is only one commercial slide from me for Hitachi. Hitachi is in the business of thermal analysis for more than 4 decades. So they have a very rich experience in thermal analysis business. And just to give you most important information to all the participants, Hitachi is always concentrating on these 3 important specification or feature which are listed below: world-class best sensitivity, world-class baseline stability and repeatability, excellent quality, and giving the 2 years warranty. So that is the confidence level of Hitachi in thermal analysis business. I will not read out all the above achievements which have been achieved by Hitachi in last 4 decades. So just to give you an idea, whenever someone is buying a DSC, differential scanning calorimeter, what he should look into? He should look into 7 important specification or features are embedded in the instrument. What is the sensitivity? What is the noise of the instrument? Noise multiplied by 2 is the sensitivity of DSC. What is the resolution of the equipment? Most of the time you will find that resolution is improved, but the sensitivity is compromised. So that should not happen. What is the baseline performance, ruggedness of the sensor, how the low temperature performance is, and what are the different software which are bundled along with the instrument. So these are the 7 important capabilities one should look into when you want to get the best data from any thermal analysis equipment. I am talking particularly about DSC right now. So just to give you a basics of DSC, DSC stands for Differential Scanning Calorimeter, wherein the heat evolved or energy absorbed is measured as a function of, just a minute, sorry. Is measured as a function of temperature when the sample is being heated, cooled down, or held isothermally. So look at the left-hand side of the block diagram. Inside any DSC, since the sample is being heated, there is a very small compact furnace is there. Inside the furnace housing, there are 2 different holders are there, sample holder and reference holder. And beneath or below them, there are 2 individual thermocouple, normally it is called as thermopile sensors, are there below the sample holder and reference holder, and you are keeping the sample in an aluminum cup, which is normally disposable. So just to give you an idea, let us assume I have kept a benzoic acid here, and I give a command to PC start heating the sample. As long as there is no change in the benzoic acid, temperature of the sample and the temperature of the reference will remain same. As soon as benzoic acid starts melting, benzoic acid melting is an endothermic reaction. As soon as this endothermic reaction starts in benzoic acid, which is kept in the sample position, these two thermopile sensor, which are just placed below the sample and reference, they will immediately recognize that melting or an endothermic reaction of sample has occurred, and then that endothermic reaction which is sensed will be further amplified. That temperature difference which is created due to the endothermic reaction will be further amplified by the electronics which is built in, and then you get a plot typically shown at the bottom, a change in energy versus temperature, which is shown here at the bottom. So in short, what you have to remember is, in case of DSC, always on the y-axis, you have a change in energy, and on the x-axis, you have a change in temperature, which is occurring in the sample. And you are measuring various properties of the sample, like melting, crystallization, glass transition temperature, phase transition, and so on. And in order to calibrate the DSC, you are using a material which is called as indium, which has got a very precise melting point, 156.6, and it has got a very precise enthalpy, which is 28.67 joules per gram. That indicates that your instrument is calibrated. Just to move further about the application, people who are working in polymer industry or polymeric application, you can see over here a single technique which is called as DSC will give you such a huge application by using a single instrument called as DSC. I will not read out each and every application here, but this slide gives you an idea how important or how powerful a DSC is a tool to study various types of polymers, various types of properties by using a differential scanning calorimeter. Those who are working in pharma industry or those maybe working in chemical industry, again, look at the list of the application. One can perform all these applications by using a DSC technique in pharmaceutical environment or maybe chemical environment. We will see few of them application during my presentation. Another advantage of DSC is used to quickly identify what type of polymer it is. So I have just listed here around 15 to 20 polymers here. And you can see here the second column, it is giving a glass transition temperature of these polymers. And in the third column, it is giving a melting point or a melting range of this polymer. So on the basis of their melting range and on the basis of their glass transition temperature, one can quickly identify what is the polymer which is present. So if you have any unknown polymer from the supplier or from anywhere, you can quickly identify that by using a DSC. Of course, other techniques are available, but DSC is a faster tool. Now, just to give you very important information, in case of DSC, many times in the research field, you are doing a very high sensitive application. You have to have the system wherein a very small or very weak transition is being determined by DSC. So on the left-hand side, you can see over here a 5 microgram of indium, which is used as a calibration material, is shown here. And look at the width of the signal. Height of the signal which is obtained is approximately 40 microwatt. That indicates a smallest sample size is producing such a high signal strength, and that is called sensitivity of the instrument also. Another application is shown here on the right-hand side. Before I forget, please remember DSC does not know what type of sample you have kept inside your sample pan. On the basis of the result, you get like endothermic reaction or exothermic reaction or phase transition or a glass transition, you have to interpret your data. So coming back to the right-hand side diagram, now this is a DSC graph of toner, a toner which is used in photocopying machine to copy your document. Now, toner is basically a polymeric material, but this you can see over here, there is a huge melting of toner polymer is there around 89 degrees Celsius. we are not interested in melting of the polymer, but we are interested in a small quantity of additives which is being added inside the sample. And if you see over here, the sample taken is 103 microgram of toner sample. In 103 microgram of toner sample, such a small additive which is present inside the toner is determined only when you have a very high sensitive DSC available at your disposal. A third application of DSC which is shown over here is many times you hear in the field, you have a recycled polymer being added in the virgin polymer. So on the left hand side, you see over here, you have a recycled polypropylene, you have a new polypropylene with the recycled material, and you have a virgin polypropylene. So there are three samples are there: recycled, recycled mixed with the virgin polypropylene, and virgin polypropylene at the bottom. Let us concentrate on the middle graph. Can you see over here? Recycled polypropylene, which is added in a very small quantity, is being identified by the circled peak, peak number 1 and peak number 2, which are expanded on the right hand side. So you can see over here, if you have a very high sensitive DSC, you can capture even the small concentration of recycled polypropylene, which is being added in the virgin polypropylene. So for a packaging industry, this can be a very wonderful application. Another application which is related with the polymer industry or a packaging industry and related industry, you can see over here, even a small concentration of polypropylene, you can see over here, 0.5% of polypropylene is added and 10 milligram of HDPE. So you can see over here, this is the major peak of HDPE. We are not interested in major peak of HDPE. We are interested in a very smaller peak, which is zoomed on the right hand side. And you can see over here, 50 microgram of polypropylene can be determined by DSC. Another application of DSC here, you can see over here, it is a polystyrene sample which is undergoing a glass transition temperature. A glass transition temperature is a second order transition. A glass transition temperature is a temperature during which a change in specific heat is occurring. So basically, glass transition temperature is also showing the amount of amorphous phase which is present in the compound. So example is shown over here for a polystyrene sample, and a glass transition temperature is obtained around 86 degrees Celsius. So this indicates it is amorphous in nature, and you can identify whether the polystyrene is present or not on the basis of DSC result. Another application which is related with the people who are working in biological field. So here the application shows a thermal denaturation of protein material. So the name of the compound is lysozyme 1% aqueous solution, which is a very, very low concentration. And this 1% of lysozyme can be determined by DSC, and the property which is measured is called as thermal denaturation of protein. A thermal denaturation means breaking of the bond. So on the basis of breaking of the bond and its temperature, one can identify what type of protein it is. Another application of DSC is DSC can be upgraded in future by a camera. So you can attach a camera on the DSC, and then when you are running the sample, the image of the sample is captured at various temperature. You can see over here with respect to temperature, image of the sample is being captured at position number 1 to position number 7. So you can look here at room temperature, look at the size of the sample. As the temperature is increased, the material is shrinking with respect to temperature, and then you can correlate the data which you are obtaining with respect to the temperature analysis using this DSC curve and correlate your data on the basis of images which are obtained. So I have shown you example for polymer, but this can be very useful for a pharmaceutical environment where people are looking for a change in polymorphs with respect to temperature. So now, up till now, we have discussed, let us say, most of the application related with the polymeric industry. Let us come back to the pharmaceutical industry. So in a pharmaceutical industry, you have a raw material characterization, a typically drug and excipient. And the typical characterization, which is carried out in pharmaceutical environment, is identification of forms, whether you are getting the same polymorph for the formulation. Hydrates and solvents, they are also treated as a polymorph. And sometimes people are interested to determine the amorphous phase which is present in the formulation or in your API or excipient and so on. And you can also correlate your data with respect to percentage crystallinity of the material. So the first application in pharma environment is determination of purity. Along with the DSC, there is one software which is available, is called as purity software. And this purity software can determine a purity of the compound directly. And that software is based on the equation which is called as Van 't Hoff equation of melting point depression. So here you can see in the slide, a Van 't Hoff equation of melting point depression is shown over here. TO is the theoretical melting point of the pure compound. Tm is the measured melting point by DSC. R is the gas constant. X2 is a mole fraction impurity which we want to determine. And delta HF is a heat of fusion or an enthalpy which is determined by DSC. So DSC will determine delta HF. DSC will determine Tm. R is the gas constant. By using this Van 't Hoff equation, one can determine the mole fraction impurity which is present in the compound. Before I show the slide, please remember, as long as your compound is more than 98% pure, this purity software holds good. The sample should have a melting, and the impurity which is present also should be soluble in the melting, and there should not be two forms of the compound, and the sample should not decompose or evaporate before melting. So these are the some restriction when we talk about the purity of the compound by DSC. And the example is shown over here on the left hand side. The name of the compound is phenacetin. Now there's three graphs are shown on the left hand side, and this is the Van 't Hoff plot is shown in the middle. And then on the table, you can see over here on the left hand side, a purity of the phenacetin is determined by HPLC, and purity of the phenacetin is determined by DSC. There is a close agreement between the HPLC data and the DSC data that indicates a DSC can be also very important tool for quick identification or quick determination of purity of the compound. The advantage of the technique is no solvent is required. The advantage of the technique is very faster technique, and you can conclude about let us say quick quality control also you can say for purity determination. Another example is shown here with the DMT salicylic acid. On the left hand side, you can see over here the purity is determined by a DSC, and on the right hand side calculated purity by some conventional technique. So you can see over here on the top two graph, you can see very close agreement between the purity of the compound determined by DSC and the calculated by purity. If the moment you go to the downward, I think there is a variation is there in the result, but as long as your compound is holding more than 98% purity, the software holds good. Another application of DSC in the pharmaceutical environment, maybe in the dyes and chemicals, is the determination of polymorphism. A polymorphism, poly means many, morph means structure. So whenever any sample is exhibiting more than two crystalline modification, that behavior is called as polymorphism. Now here the example is shown for the carbamazepine. A carbamazepine is a compound which has a total 18 polymorphs, and one of the polymorphs of this carbamazepine is shown over here. So how the polymorph is being interpreted? Your sample is kept at room temperature. Around 174, your compound is melted. And during the melting, the compound is immediately crystallized into another form. And on further heating, the second form which is crystallized during the first melting, you can see over here a second form is melting. So this is how a polymorphism is being expressed in pharmaceutical environment, or people who are working in dyes and so on. There also we understand a polymorphism is being experienced. Just to give you another example, like for example, chloropropamide. Now this chloropropamide has got four polymorphs, form 1, form 2, form 3, form 4. This is the DSC graph. Now look at the graph. The graph itself is so very simple to understand. Now I will show you the same graph, then same sample for their XRD data, because polymorphism is normally determined by most of the time by XRD also. Now look at the XRD data in the next slide. Can you see over here? Look at the graph. Unless you have the knowledge of 2 theta values for the different polymorphs, then and then one can interpret this XRD data. So in order to interpret the XRD for the polymorphism application, one should have an expertise in X-ray diffraction technique. But if I coming back to the previous slide, you can see over here, even by looking at the temperature region where the polymorphism is being experienced by these 4 different forms of chloropropamide, is a very easy technique as compared to XRD technique. That does not mean I am criticizing here X-ray diffraction technique. Another application of DSC is on the left hand side, you can see over here form 1, form 3 and form hydrate. Can you see over here? These are the 3 forms of carbamazepine. Now, if for the formulation, if you have decided to use form 3, so you are getting consistently form 3 from your supplier or not, or from vendor or not, you can quickly identify by using DSC. Many times, hydrates is treated as a polymorph. So whether hydrates is there or not, because if somebody has used hydrate for particular formulation as a patent, you cannot copy that design. So at that time, even DSC can be very versatile tool to quickly identify whether the hydrate is present or not. On the right hand side, you can see over here, what is the effect of grinding on the polymorphism. So if you look at the graph, milling means grinding. If there is no grinding of the powder is taken place, you have a single peak you can see over here. 5 minutes of grinding, you can see over here, a small change have occurred in your polymorphism. 60 minutes of grinding, you can see over here, your crystals are destroyed and some unknown behavior is seen. So by using DSC, one can also study what is the effect of grinding on my original polymorph. Another advantage of DSC is you can calculate the peak area, and the peak area is always expressed in terms of joules per gram. So if you have some known pharmaceutical compound or a pharmaceutical API where you already know what is the crystallinity of that particular API, on the basis of joules per gram, you can also correlate what is the crystallinity of the unknown material you are getting on the basis of reference material which you have in your laboratory. Another application of DSC in the pharmaceutical industry is, this is again a protein application. You can see over here, 1% of insulin solution. Insulin is undergoing a phase transition. So you can see over here, the phase transition which are occur on the lower side as well as protein denaturation studies. So on the basis of the protein denaturation studies and their temperature behavior, you can also identify the insulin material by using a DSC. Another application which we discussed a couple of minutes back was about the glass transition temperature. As I told you, glass transition temperature is the temperature below which, now this is the glass transition temperature, a temperature below which material is brittle and temperature above which material is flexible. So this is the definition which is typically used in polymer industry. As far as people who are working in physics and other thing, this is the transition which is called as second order transition. This is a very, very big transition sometimes, and you have to have a very good sensitive DSC to record this transition. And this is the transition during which a change in specific heat is taking place. And on the basis of change in specific heat value, you can also quantify how much amount of amorphous phase which is present in the compound. As far as pharmaceutical industry is concerned, now this is the API you can see over here, CLP. And why amorphous phase is very, very important in pharmaceutical environment is because amorphous phase is directly related with the solubility, directly related with the processability. If there are any patenting issues are there, you can address the patent issue. And as far as the compressibility of the tablet is concerned, also amorphous phase present is very, very critical. Another application is shown over here. Many times you hear the news in the market, some counterfeit drugs are being captured or being confiscated. So DSC can be very versatile tool to identify whether the drug is original or is it a counterfeit drug. And this is the sample. There are different batches of illegal or illegal benzodiazepine are shown over here. And on the basis of their melting behavior, you can identify which one is a counterfeit and which one is not a counterfeit drug. So you can imagine, we are only discussing about DSC now, and we are discussing about the variety of application which can be implemented by DSC. Another application of DSC in the pharmaceutical environment is called as compatibility. Compatibility studies by DSC. The excipient which is used along with the API, whether it is compatible or not. Now there are 5 graphs are shown over here, superimposed on the single screen. And here the material which is taken is an antiviral drug which is shown as ACV. Now look at the top graph, antiviral drug only. There is a clear-cut melting of this antiviral drug compound around, let us say, 250 degrees Celsius. Now let us look the another excipient which is added, which will be used, is called as lactose. Lactose has the 2 melting, which is shown here in the second graph. The third excipient which is added is called as methyl cellulose. which is having a very broad melting region. And then what pharmaceutical industry wants to know, which excipient will be compatible and which one will not be out of this lactose, CMC and colloidal silicon dioxide, where there is nothing is there. Now look at the ACV with the lactose. Let us look at the graph number 5 from the top. I am just moving my cursor. This is due to the melting of lactose. Now this is again due to the melting of lactose. And now look at this. My ACV, that is my antiviral drug, I did not see a melting of this antiviral drug. That indicates this lactose is not compatible with ACV. But if you look at the methyl cellulose, you can see over here, you clearly see the melting due to the antiviral drug, signifying that there is no interaction between methyl cellulose and the antiviral drug, while in case of lactose, there is a clear-cut interaction between the lactose and antiviral drug that indicate it is a non-compatible. So like this, you can determine the compatibility of drug with the excipient by using DSC. The advantage of the DSC is it is an accelerated tool. The information which you have obtained here is less than 20 minutes. Otherwise, by using some conventional technique, sometimes you have to wait for 6 months, 9 months to identify which one is compatible and which one is not compatible. Another application of DSC is the lithium-ion battery. Nowadays, we hear in the market about the electrical vehicles, and many manufacturers are switching over to lithium-ion battery. So in lithium-ion battery, they are using a polymeric membrane, which is called as separator membrane in 2 electrodes. So if you want to quickly identify whether you are getting the same membrane during the manufacturing process or it is being used, you can use the DSC. The advantage here is, even if you have such a small thickness membrane, just imagine 18 micron thickness membrane is being used in the manufacturing process, and such a small thickness with such a small sample size, you can see over here a clear cut melting of that membrane which is used in lithium ion battery. So the advantage here is, if you have a very sensitive DSC, then and then you can determine such a small thickness material and having a small sample size by DSC for its identification. Next application is shown here, again related with the battery material. Now in battery, you have having the electrodes and you have the electrolytes. Now you can look here at the left hand side. Now this is only DSC result of electrolyte. On the right hand side, a cathode material along with the electrolyte is being used. And if you look here, when the cathode material comes in contact with the electrolyte, the type of reaction which is occurring is a strong exothermic reaction. You can see over here, exothermic reaction is being occurred. So people are developing the electrolyte along with the cathode material on the basis of this exothermicity, so that we do not have a maximum failure in the field related with batteries are burning or batteries are exploding. So this is another application in DSC which is being used in the battery industry to quickly identify the safety hazard analysis of a battery material. Another application is shown here for the rubber material. Why I have selected rubber? Because a couple of, let us say not couple of, around 2 years back, the whole world was suffering from corona and we were using the vaccine. And on the top of the vaccine, the material which is used through which injection needle was pierced was a rubber material. And that rubber material should be a consistent from batch to batch. So DSC is very useful tool to quickly identify whether you are getting the same rubber material. The most important parameter here is most of the rubbers, they have a glass transition temperature much below room temperature. You can see over here, a glass transition temperature is around minus 62 degrees Celsius. So quick identification of the rubber which is used, it need not be a vaccine, but a vaccine bottle. It can be for any application. It can be a tire industry, it can be a rubber industry, it can be automotive industry, it can be steel, it can be various applications wherein rubber is being used. So if you want to quickly identify whether you are getting the same rubber material, DSC is a very versatile tool. Another application in DSC is typically related with the graphene material and the low temperature and the polymeric material. So you can see over here on the left hand side, these are some nanomaterials are there, where in the melting of that nanomaterial polymeric material is shown over here. And on the right hand side, the graphene material, wherein the melting is occurring much below room temperature. So on the basis of this melting of this graphene type or certain nanomaterial, you can quickly identify by DSC, even though the transitions are much below room temperature. Another application of DSC, of course, this slide should have been the first slide. DSC is a very versatile tool to quickly identify what type of polymer it is. So we have already seen one chart wherein I have listed or I have shown you different polymers and their melting range. Now look here, polyethylene, polyacetal, PBT, nylon 6x6, and polythalamide. By just looking at the graph, one can make out what type of polymer it is. So that is the advantage of DSC. You don't need a very specialized knowledge to quickly identify whether it is an nylon 6x6, whether it is a polyethylene or a polyacetal, and so on. So DSC is a very versatile tool, very quick tool to quickly identify what is this polymer is on the basis of their melting range. And this melting range is well defined in the polymer handbook which we have. Another application of DSC is that quick identification of course, polymer is shown over here, LDPE and HDPE, because these are the two polymeric material which are very widely used in packaging industry. So on the basis of their melting profile, LDPE and HDPE, you can quickly identify what type of polymer it is. Even if there is a blend of LDPE and HDPE is there, you can also identify whether the supplier is giving you the same blend material from batch to batch and so on. Even if you have a LDPE, you have a LLDPE, you have a HDPE, you have a MHDPE, these four different types of polymers which are typically used in packaging industries can be also easily identified by DSC. At that time, instead of using the heating technique, sometimes you have to use a cooling technique to quickly identify is it LLD or LD or MHD or HDPE by using the crystallization behavior of the polymeric material during the cooling cycle. If recycled material is added, we have already discussed, so you can see over here a small amount of LDPE is added in HDPE. You can quickly catch the vendor. You are not supplying the virgin material, but you are supplying the recycled material. You can catch the vendor. Another application of DSC, people who are working the research, and if they want to know what is the effect of nucleating agent or the additive which is being added in the polymer. Now, this is the example of polypropylene crystallization. Now, this graph is with respect to time. The sample is heated up to 150 degrees Celsius. At that temperature, 160 perhaps, at that temperature, the crystallinity of the polypropylene is totally destroyed and then cooled down rapidly to 125 degrees Celsius. And by bringing down to 125 degrees Celsius rapidly, hold isothermally. Now you can see over here, sample A and sample B. Look at the crystallization behavior. Whenever peak is in upward direction, it is an exothermic reaction before I forget. Now look at the sample A and sample B. There is a total difference in the behavior of the crystallization of a polypropylene at 125 degrees Celsius. This is a very useful information. Many polymer technologists or polymer scientists are looking for what is the effect of additive or what is the effect of nucleating agent on the crystallization behavior of the material can be also studied by DSC. This is called as isothermal crystallization study. People who are in the pharmaceutical industry, they are exporting their drugs or their pharmaceutical products. If you go to USA, in USA, the tablets are never sold in aluminum strip. The tablets are always sold in a HDPE small bottle. So for them, the bottles which are coming from India, whether the bottles are of correct quality or not. So there is one USP method is there, which is called as USP 661. And on the basis of USP 661, you have to quickly say whether the material is same or not. Another application of DSC is in the adhesive industry or a paint industry. You can see over here how my cross-linking is taking place with respect to temperature or with respect to time, my apology. You can see here, I have taken the adhesive. It is totally uncured. As the time progresses, after 1 day, my material is completely cured. And the curing of the material is determined on the basis of glass transition temperature. So you can see over here, as the time progresses, how my material is getting cured with respect to temperature. So curing kinetics or extent of cure can be determined by DSC. This is a very good example is shown over here, epoxy material which is used in the adhesive. And if you look at this is the base compound, this is epoxy. This is the curing agent, graph number 2. Graph number 3 is a curing agent plus epoxy compound. And after this, you can see over here the material is cured, and curing is always expressed by the parameter which is called as glass transition temperature. Another example of DSC, another application of DSC is in the fat industry, oil industry, and chocolate industry. Now, this is the example of chocolate is shown over here. Now, look at this peak, which is around 25 degrees Celsius. Now, this peak is related with the particular form of cocoa butter, because the major constitution of chocolate is cocoa butter. So, whether you are getting the same cocoa butter in the chocolate, it is very quickly determined by DSC, because the texture of the chocolate, when you put the chocolate in the mouth, the texture of the chocolate will be felt when you are eating the chocolate, and that is decided on the basis of the polymorph which is being added in the chocolate sample. Lipstick sample, even the lipstick can be quickly identified by DSC, because in lipstick you are using the wax. It can be a paraffin wax or it can be a microcrystalline wax with the paraffin wax mixture. So whether you are getting the same quality of wax mixture in lipstick or not, whether the manufacturer has used the same quality or not, you can quickly identify by a DSC. You can see over here a lipstick batch number A, batch number B, and look at the difference in the first run and the second run. And this can be a good quality control tool for people who are working in lipstick industry. Another software which is coming along with the DSC is called as temperature modulated DSC. So on the left hand side, you can see over here a graph which is generated by giving a sinusoidal treatment, a sinusoidal modulation to your compound when it is being linearly heated. Because whenever your sample is exhibiting linear heating as well as sinusoidal treatment, you can generate the graph by using the MDSC software. And on the right hand side, you can see over here a non-reversible transition, a reversible transition, and total heat flow can be seen here. The advantage of the technology or advantage of the software is it is enabling you to separate these two transition, reversible transition and non-reversible transition. So how it can be useful for the common or different application. On the left hand side, you can see over here, this is the non-reversible flow, which is related with the enthalpy relaxation. And if you look at the reversible flow, reversible heat flow, it is a glass transition temperature. Now, if you see the DSC graph, which is in the middle, you do not know is it a stress relaxation or enthalpy relaxation, or is it a glass transition temperature. But if you have the capability in the software to separate these two transition, you can quickly say my glass transition temperature is camouflaged during this enthalpy relaxation which has occurred in the pharmaceutical compound. In a similar fashion, you can see over here, it is shown in the adhesive industry. If you look at the middle graph, you are not able to savor the glass transition temperature very clearly. But if you see that reversible and non-reversible, you can quickly identify this is my glass transition temperature and or glass transition phenomenon, and a non-reversible that is called cross-linking reaction. Another example is shown for the paint industry, a coating of the film. So the film is being shown here on the left-hand side, and when it is exhibited for the MDSC, a non-reversible heat flow and reversible transition. Glass transition temperature is a reversible transition. I forgot to inform you. And this non-reversible transition here is evaporation of the solvent, because in the paint we are using the solvent, and the solvent is getting evaporated. That evaporation temperature is exactly matching with the glass transition temperature. So normal DSC will not be able to separate whether it is due to the evaporation or is it due to the glass transition temperature. But MDSC software is separating these two phenomenon, which are competing phenomenon. Another advantage of DSC is you can determine directly specific heat of the compound. By using the modulated DSC, you can see over here a delta Cp with respect to temperature is determined by DSC. So no need of performing 3 experiments. Normally in DSC, a specific heat is determined by a procedure which is called a 3-step measurement. First, you run the empty pans, then you run the sapphire, which is the reference material for the specific heat calculation, and then run with the sample. Now, empty pan, sapphire, and your sample is superimposed on a single screen. And then these 3 graphs can be exported to the specific heat software, and then it will determine the change in specific heat which is occurring in the sample. The disadvantage here is you have to perform 3 separate experiments for a sample. But if you have a modulated DSC software, this can be minimized to only single step. So that is the advantage of modulated DSC software. Many times you see in the field nowadays that whenever you are traveling on the road in India, you might have observed that optical fiber cables are laid down. And this optical fiber cable are laid down in a colored pipes. So you might have noticed some colored pipes are being used to lay down the optical fiber cable. And in order to test this pipes, which are normally made up of HDPE, the test which is recommended by ASTM, it is called as OIT test, oxidative induction time test. And now this is the time. Can you see over here? It has taken more than 70 minutes to degrade. So more than 35 minutes is treated as a good pipe because this test is carried out 200 degrees Celsius in a pure oxygen atmosphere. It is not carried out at room temperature or other temperature. So you heat the polymer, go to 200 degrees Celsius, switch over from nitrogen to oxygen, and then determine how much time it is taking to degrade the polymer. More than 35 minutes is taken as the good quality of HDPE pipe, which is used for the optical fiber cable. This is the safety hazard analysis. So many times you hear in so and so factory explosion have taken place. That explosion is taking place due to the in situ reaction, which is occurring in your reactor or inside the vessel. So to determine at what temperature my exothermic reaction will start, at what temperature my exothermic reaction will end, so that particular chemical can be studied by using a DSC technique. You can see over here, this is a strong exothermic reaction starting at this temperature, starting here, and the amount of enthalpy which is liberated. Now, if you have a software, you can see over here how my area is changing with respect to temperature and how my percentage of reaction is changing with respect to temperature. So this useful information can be gathered for determination of safety hazard analysis of your chemical reaction. So another example is shown, same example is shown over here. You can cut the graph by using the software. These are the slices, and you can determine how much percentage of reaction have taken place at various temperature, which can be very valuable information people who are working in safety hazard analysis. And then you can also do a kinetics of this previous exothermic reaction, which is shown over here. By running the sample at 3 different heating rates, you can generate the kinetic data, and this kinetic data will give you a lot of information with respect to time, with respect to temperature, with respect to percentage reaction, and so on. Due to the paucity of the time, I cannot show you all this data. This is the slide which is showing the quick identification of rubber. You can see over here a nitrile rubber, SPR, urethane rubber, and epoxy resin rubber. And look at the glass condition temperature. By looking at the glass condition temperature, you can quickly identify rubber A, rubber B, and rubber C, and rubber D, and their respective identification by DSC. This is the PCM, phase changing material. A phase changing material is a material which is releasing or absorbing the mineral energy at phase transition. So the amount of energy which is liberated or absorbed during the phase transition is very, very critical for various applications wherein heating or cooling is involved. Now you can see over here, there are 3 different types of phase changing materials are shown here: eutectic salt, metal alloys, and paraffin. There you can see here the enthalpy which is liberated, melting, which is seen over here in case of material. Now, this enthalpy is very critical for people for devising the application of this PCM material. Another application is shown over here for HDP and paraffin wax mixture. This is also a PCM material, a phase changing material. And you can quickly identify, first of all, is it the same PCM material mixed with the paraffin and HDP or not, and the amount of enthalpy which is liberated. In DSC, DSC can be in future upgraded to a UV spectrometer or a UV radiation. The advantage of this polymer is shown over here by using the DSC. Another important parameter you should remember is in DSC, there are different types of crucibles are there. Unless you select the correct crucible, you cannot perform the correct application. So knowledge of selection of crucible is very, very important when you are buying DSC. So these are the high pressure crucible on the right hand side, used typically for the safety hazard analysis or explosive sample or exothermic reaction. In the middle, you can see over here the low pressure crucible, wherein you are suppressing the evaporation reaction of the solvent or maybe the moisture. And these are the normal crucible of different material like aluminum, ceramic, copper, platinum, and so on. So knowledge of selection of crucible is very, very critical. So we'll go to now TGA, thermogravimetric analyzer. So again, what are the parameters you should remember when you are buying a thermogravimetric analyzer is shown over here. What is the sensitivity of my instrument, whether my balance housing is having a temperature control or not, because this is very, very important. The type of balance which is used in any thermogravimetric analyzer is having the sensitivity of 0.1 microgram or 0.2 microgram. What is the repeatability of my balance? Most important parameter, because if you want to perform a quantitative estimation very accurately, the balance has to have a good repeatability. Then and then you will be able to determine a small concentration of particular additive or particular material which is being added in your compound. What is the accuracy of the balance? So these are the all important parameter. If you have additional flexibility in your TGA to measure DSC, will be very ideal. So when we see some application, it will really give you additional information and how quickly the furnace is cooling down, whether my gas can be introduced near the sample. So these are the important parameters which are offered by most of the manufacturer, but you should look into this parameter when you want to get a good quality TGA in your laboratory. So how the TGA works? Of course, this is the Hitachi diagram. The principle remains more or less same except horizontal design and vertical design. So you have a furnace which is shown on the left hand side, and you have a balance mechanism which is called as ultra micro balance. Now you can see over here, this is the dual beam technology. The sample is kept in the one holder and reference holder is always empty crucible in case of TGA. Now you can see here, let us take the example of calcium oxalate with single water molecule. So I have kept calcium oxalate with single water molecule. As soon as water molecule which will lose around 125 to 130 degrees Celsius, this beam which will go down slightly due to the evaporation of the solvent or loss of solvent, that is called water. As soon as this beam goes down, the beam is directly connected in the ultra micro balance to a device which is called as sensor or detector. These are the optical sensor. So this optical sensor will be displaced from its position the moment evaporation of moisture takes place. Now what happens is that the moment this displacement of detector or a sensor takes place, in every micro balance or ultra micro balance, there is another component is there which is called as fulcrum coil, drive coil, or electromagnetic coil. This electromagnetic coil will start giving current in such a fashion that this sensor is brought back to the original position. That amount of current which is given in milliampere or microampere is directly proportional to the mass change which is occurring in the sample. So this is how TGA works in most of the system. The TGA is calibrated by using the melting material. Melting, so you can see over here, indium, lead, aluminum, gold, palladium, depending on the temperature range. So we'll discuss about the various applications of TGA now. For the first application, you can clearly see here, different polymers have an onset of decomposition. By looking at the onset of decomposition temperature, you can make out, is it a PVC, is it a PMMA, is it a HDP, is it a PTFE, or is it a polyimide? So this is the first easy application. The second application of TGA is typically used for determination of composition of the material. Here the example is shown here for the automobile industry. In automobile industry, you are using a different types of material like a cleaner hose, a wiper hose, windshield gasket, door gasket. There are so many parts which are going in automobile industry nowadays. And their quality control is very, very important because all these automobile industry, they do not manufacture this small attempt. They are getting it done through the vendor. Whether the vendor is giving the consistent quality or not, they can check on the basis of TGA graph. How much is the volatile content? How much is the polymer content? How much is the carbon black content? And how much is the ash content? Will enable them to identify quickly about the quality control. Another example is shown here for the pharmaceutical environment or maybe another chemical also. Here, what is important is how much amount of water content is there. Now, can you see over here? This is the TGA plot showing 0.2% of moisture content. 0.2% is equivalent to 2000 ppm. What is important is one of the specification which I told in the previous slide, how baseline stable is at higher temperature will enable you to quickly identify, not quickly, but accurately identify the moisture content. Now, another feature which I had told you in the previous slide, if you have a flexibility to actuate a DSC signal in your TGA, you can see over here, you can quickly identify, yes, it is the phenacetin because this is the melting of phenacetin. This graph need not be taken every time, but if you have any particular application or particular thought, whether you want to see whether my melting is being seen or not, you can also generate this graph by using a TGA. Another application is shown over here is how much is the free moisture content and how much is the bound moisture content. Because by using the Karl-Fischer apparatus, you are only determining total moisture content. You can see over here adsorbed moisture and the bound moisture. Bound moisture is the moisture which is attached to your ligand, and free moisture which is adsorbed on the surface. Another application is shown here for the CNT, carbon nanotube. Here the material is polypropylene, and in this polypropylene, a small carbon nanotube is added. So can you see over here? This is the decomposition of polypropylene, which is 97.8%. But what is important is not the 97.8%, how much amount of carbon nanotube is there. And this carbon nanotube 2% is very accurately determined by using a TGA. You can see over here, the 2% is corresponding to 104 microgram. Now look here, the weight of the sample taken is 5 milligram. So in 5 milligram, 2% is approximately 100 microgram, 105 microgram. So if you have a good baseline stability, repeatability, you will be able to see such critical application in TGA. Another application of TGA is, you can see over here, a decomposition of HDPE. And many times you are not interested in only HDPE decomposition, but if you want to quickly identify, is it really HDPE or not? Just actuate the signal of DSC and TGA, and you can quickly identify, yes, it is a HDPE on the basis of melting transition. Similarly for nylon 6, because nylon has got multiple grade. Nylon 6, 6x6, nylon 66, nylon 6x12, and so on. So it is very essential to also know what grade of nylon I am using in my automobile industry. And if you have a TGA graph, you can see here, this is the nylon content, and this is the volatile content in my nylon. But if I can actuate my DSC signal, I can quickly identify whether I am getting nylon 6, 6x6, 66, 6x11, and nylon 12, and so on. So this is the very general slide to determine the PVC content. How much is the DOP content? How much is the POC content? How much is the filler content? This is the analysis of polyvinyl chloride pipe or something like that. So very quick identification, quick composition determination by TGA. Another application is shown here. Many times nowadays we see beer or a soft drink is packed in an aluminum can. So these are the aluminum cans, but these aluminum cans are coated with the polymeric material inside. So what we have done is the small coating is taken out in the pan, and then it is analyzed by TGA. Now look here, the weight loss up to 600 degrees Celsius in air is, let us say, 23.5 microgram. Now this weight loss is directly correlated with the thickness of the material. You cannot afford to have too much thickness inside this can. And you cannot afford to have too thin thickness, because the thickness is too thin. Maybe the packed drink like a soft drink or a beer will not have a shelf life, and too thick, more money. So in such cases, the thickness of the polymer can be correlated with the TGA studies. This is a very general slide. How much is the oil content, how much is the polymer content, and how much is the carbon black content. Whether the material is added with the flame retardant or not. So you can see over here, without flame retardant, the graph will look like this. And with the flame retardant, the graph will look this. Flame retardant is a material additive which is being added in a cable industry, in the polyurethane, in automobile industry for certain parts. The advantage of flame retardant is it will retard your catching the fire. So many times you hear that the cable is catching the fire. Maybe there is a possibility a proper amount of flame retardant is not being added. So whether the proper amount of flame retardant is added in the cable or a polyurethane material, you can quickly check by a TGA technique using air atmosphere. Another example is shown over here for a neoprene rubber and a rubber blend. So you can see over here, you can quickly identify an NR and a neoprene rubber by using a TGA technique, which is useful particularly in automobile industry, because in automobile industry they are using different types of rubber material. Sometimes they have to use the polymer blend, and which type of polymer blend is being supplied by the vendor, for them it is very, very critical. So TGA is a very versatile tool to quickly identify whether it is a natural rubber, neoprene rubber, butyl rubber, EPDM rubber, and so on. Volatility of the oils, you can also determine the volatility of the oils by using a TGA on the basis of the onset temperature you can identify is it a paraffinic oil or a aromatic oil or a naphthalene oil. This is a very wonderful application of TGA. Many times we use in washing machine the softener, which is called as Comfort. Of course, Comfort is the Indian brand, and nothing to do here with the Comfort. But what is important here is if you have washed your material in a washing machine with the softener having some fragrance, how long that fragrance will remain once you wear that clothes. Now, can you see over here? This fabric is held at 50 degrees Celsius almost for 500 minutes. You can see over here, it is losing a 0.1% over a period of almost 500 minutes. That indicates you will have a feel of that fragrance when you are wearing the clothes, at least for a couple of hours, definitely. So such applications are also carried out by TGA. So there is another test which is called as a NOAC test. Engine volatility. So engine volatility is determined at 250 degrees Celsius for 1 hour. Okay. Now, NOAC test is related with the Euro norms, that is the emission norms. Nowadays, we hear that all vehicles which are manufactured in India should follow Euro 6 or Bharat 6 norm. And to ensure that the lubricating oil which is being used, lubricant which is used, is it following that norms or not? And the test is performed by TGA. You can see over here, the material is, the oil is held at 249 degrees Celsius in air atmosphere. And you can see over here, this is your reference oil, and the weight loss is determined at 249 degrees Celsius, and the weight loss should not be more than 14.5 or 14.9%. That indicates that your oil quality which is used in your vehicle is good, and it will follow the Euro 6 norm as well as Bharat 6 norm. TGA along with the DSC mode can be also used for direct determination of specific heat. The example is shown here for the determination of specific heat by using a modulated DSC mode in the TGA. You can also have a simulation. So if you are running the sample at 10 degree per minute, run the sample at 100 degree per minute. This is not applicable for each and every sample. And you can see how the simulation graph will look like at 10 C per minute. Now this will enhance the productivity of your analysis when you want to have a more number of samples being addressed. So there is no need to run at 10 degree or 20 degree per minute. You can run directly sample at higher scanning rate, and you can simulate your graph, how it will look like at 10 degree per minute or 20 degree per minute. So this is called as simulation software. We have a built-in software. We have a software which is called as kinetic software in TGA. A kinetic software in TGA is typically used in polymeric industry to determine the shelf life of the material. So you can see over here, on the basis of kinetic energy calculation, you are determining a lifetime of that material, typically in the tire industry, where they want to know how many kilometers you can use very safely by using a particular tire. Well, this is my last but one slide. So up till now, we discussed about DSC and TGA, and now we are coming to the last slide. What are the best practices one should follow in thermal analysis? One should use always small sample size. Small sample size will ensure there is a good thermal contact between your sample and the temperature sensing device. Sample has to be encapsulated properly in DSC. Starting temperature should be well below the expected transition. It is always advisable to use the 5 degree, 10 degree, 20 degree per minute low scanning speed to get the good information. Instrument should be calibrated once in a month or once in a 2 months and so on. That protocol has to be designed by the individual laboratory, which is as per your good laboratory practices protocol. You have to use always nitrogen or argon. Always system has to be always purged. You cannot use the DSC or TGA without purging, and you should not perform decomposition in DSC. This is the common problem faced in many countries, nothing to do with the India. Unnecessarily, many of our customers are running the sample up to 300 degrees Celsius when they know their transition is only at 150 degrees Celsius. Please do not allow your sample to decompose in DSC. You will damage your sensor. Nothing to do with the Hitachi. It is true for all the manufacturers. So please note this important information. And thank you very much. This is my last slide. So thank you very much for a very patient listening. And the session is open for question answer.
Thank you, Dr. Jain, for such an informative talk on thermal analysis. Hope this will help our participants in using the techniques and our newly installed facilities to the fullest. Some of the participants have some queries, so let us discuss them. How long the term stability of a emulsion or nano fluids is determined using DSC?
So stability in DSC is determined if it is related with the temperature. It can be determined in two ways. Number one is you perform the analysis dynamically and see at what temperature your material is decomposing or degrading. Another parameter which is normally studied in stability is by holding the material at isothermal temperature. So if you know in advance at what temperature you want to study the stability, you just hold isothermally and you can perform the stability of the material. The third thing which you also should remember is whether you want to determine stability in nitrogen or whether you want to determine stability in air. So accordingly, you have to switch over the atmosphere from nitrogen to air at the desired temperature when you are performing isothermal stability. So these are the things I can tell.
Okay, sir.
Unless they have some specific in emulsion, whether you want to study in presence of the solvent which is there, then you have to select a proper crucible and see whether in presence of solvent, what is the stability of the material by using a hermetically sealed crucible. Then there is no need of then oxygen to be used. That is another way of studying a stability of emulsion.
Okay, sir. Next question is why the glass fibers don't degrade in TGA analysis?
Because glass fiber has stability beyond 1000 degrees Celsius or maybe even 1200, 1500 degrees Celsius. So that is the reason it is something like ash. Because for example, you have a zinc oxide, you have a carbon, sorry, any oxide, it will not decompose. So carbon fiber, is it carbon fiber or glass fiber?
Glass fiber, sir.
Glass fiber. So glass fiber is stable up to 1000 degrees Celsius. So whatever is left over is a glass fiber. Typically, for example, you have a nylon pulley. A nylon pulley, nylon content is let us say 66% or 70% and 30% is glass fiber. This is a typical application which is used in automobile industry where they want to test the nylon pulley by using a TGA technique to identify a nylon content and glass fiber content.
Okay. So, sir, next question is whether heating rate has effect in the result of quality in TGA?
To some extent, yes. Definitely, if you run at 10 degree per minute and if you suddenly increase to 50 degree per minute, naturally your onset will change. But the composition will not change. The amount of degradation will remain same. But onset will change because if you have calibrated your TGA with, let us say, 10 degree per minute or 20 degree per minute, and you want to suddenly go to 50 degree per minute, yes, the onset temperature may change, but the composition will not change.
Okay, sir. Just one more question. How to identify the melting peak corresponding to additive added?
How to determine means you simply run in DSC and you will get the melting of additive. That's it. There is no special technique is required. You put the sample in the aluminum crucible, crimp it, and put it in a DSC. So if your melting of additive is below room temperature, you start from -70 or -170 and see at what temperature melting is occurring. Melting is an endothermic reaction. So you will see the peak due to the melting endothermic reaction.
Okay, sir. Sir, there are some questions for DSC also.
Yeah,
can DSC be used for studying protein stability studies? And
yeah, that's what I said. That's what I said, protein denaturation. So you have a protein sample and you run the protein sample and you can determine at what temperature protein is denaturating or a protein, what do you call, denaturation or protein peak is being seen, which is called as phase transition. So DSC is used for protein studies, protein denaturation studies more precisely.
And which important factor needs to be taken care of while doing so?
You have to use a specialized crucible. So whenever people who are interested in protein studies or protein denaturation studies or protein analysis, you cannot perform with a normal aluminum crucible. You have to perform with high pressure crucible. This is very, very important. So protein studies are normally carried out in presence of high pressure crucible, not normal crucible. The advantage of high pressure crucible is you are suppressing the evaporation of the solvent which is present in the protein because protein is normally most of the time a liquid solution.
This is the last question. Just wait a minute, sir. How can one analyze the supercooling or microstructural change during cooling by DSC plot?
Supercooling means it all depends on what cooling rate they want. Okay. If they are happy with 10 degree per minute or 20 degree per minute or 30 degree per minute, instead of using the intro cooler or a freon compressor, you have to use a liquid nitrogen accessory. So what will happen is your heating block of DSC is at minus 170 degrees Celsius. When you are, let us say, at 200 degrees Celsius. So when you have such a huge difference of temperature from 200 to minus 170, naturally, if you give a command to PC, it will cool down faster. But supercooling means if he is looking for 200 degree per minute or 300 degree per minute, no, that supercooling may not be possible in DSC. Depending on the DSC, again, I do not want to say any particular comment.
Hello, sir. This is Nutan. So there is one more question from one of the participants. It says he's asking, or she rather, while measuring specific heat by DSC, why is it required to record the data during heating as well as cooling? And second question is, finally, if I need to mention the single value for specific heat at a particular temperature, say room temperature, then which value to consider, the one during heating or the one during cooling cycle?
As far as heating cycle is concerned, we have seen one slide that you can perform 3-step specific heat determination. One is empty pan, second one is sapper disk, and third one is your sample. So this 3-step specific heat determination will give you change in specific heat with respect to temperature. So this is the first answer to question. In a similar fashion, if he wants to perform in the cooling mode, he can use the same methodology, empty pan, sapper disk, and what do you call sample. So as far as heating and cooling is concerned, I never heard about the cooling. People are determining specific heat. I'm not 100% aware about this part, but in heating, yes. Now coming back to the second question, if you want to determine at 50 degrees Celsius, maybe just hold a sample at 50 degrees Celsius and perform the empty pan sapphire disk. I don't know whether it is really being done, but you can calculate. Otherwise, the best way is if you want to determine the specific heat at 50 degrees Celsius, you can start at minus 20, determine the specific heat from minus 20 to, let us say, 100 degrees Celsius, and calculate how much is the value at 50 degrees Celsius. That can be another way.
Okay, thank you. Yeah, but I also have one more question. In a normal DSC, generally many of the students or users, they ask for heating as well as cooling cycles and 2 or 3 cycles of heating, cooling to be done. So is there any specific reason to do this? Like
heating, cooling, heating, typically people who are working in the polymeric industry, they will ask, because in the first heating, you are releasing the stress realization or whatever thermal history of the polymer is there, that thermal history of the polymer is being released in the first heating. Then you cool down and again rerun second time. So in the second run, you are basically getting a data which is free from your thermal history or which is free from stress realization.
Okay.
Again, there are other people who are working in PCM, that is the phase changing material. For them also, this is very, very important to study a multiple heating cooling cycle and see the behavior of the phase changing material with respect to temperature, depending upon the end application for which they are using.
Yeah. Thank you so much. Okay, if we have time for one more question, one last question.
Yeah, I have time.
Maybe.
You can go ahead. You can go ahead. Go ahead.
So there is one more question. How DSC will be useful for coated gold nanoparticles and non-coated gold nanoparticles?
DSC may not be useful because the temperature melting of the gold particle is about 1000 degrees Celsius. So DSC, most of the commercial DSCs available in the market are going up to 700 degrees Celsius. Then you have to go for a DSC which can go beyond 1000 degrees Celsius. If the gold nanoparticles which are used are undergoing a melting transition, then you have to go for a high temperature DSC.
Thank you very much.
Thank you, sir. Thank you, sir, for addressing the queries of the participants. On behalf of SEF CRNTS, IIT Bombay, I would like to thank Dr. Jain for such an interesting talk and on DSC and TGA and its applications. I would like to thank our head, Professor Suparna Mukherjee, and our SEF CRNTS team members for their continuous support in this webinar series. Last but not the least, I thank all the participants for attending this webinar and making this event successful. A link for the feedback form is shared in the question and answer section. Please do fill the form. Your valuable inputs are important to us.